In this section, you will learn about change of state of matter. There are three states of matter, namely solid state, liquid state, and gas state. When a solid is changing to a liquid, we say it is melting. When a liquid is changing to a gas, we say it is vaporizing. However, when a gas changes back to liquid, we say it is condensing. Okay? And when a liquid is changing back to solid, we say it is freezing. The temperature at which melting or freezing occurs is called melting point. And the melting point of ice is 0 degrees Celsius. The temperature at which vaporizing or condensing occurs is called boiling point. And the boiling point of water is 100 degrees Celsius. In this section, you will learn the cooling curve of wax. Wax means lab. First, let's put a test tube containing wax under the hot water bath until all the wax is melted to become liquid at a temperature of about 90 degrees Celsius. Then we take out the liquid wax from the water bath and insert a thermometer into the test tube to measure the temperature. When the liquid wax is cooling down, the temperature against time graph is plotted. When the liquid wax is cooling down from 90 degrees Celsius, its temperature time graph has three sections. The first section shows that the temperature of the wax decreases with time. The next section shows that at a certain time, the temperature of the wax remains constant. Okay? And after that, the temperature drops again. In the first region, the temperature of the wax decreases. Therefore, the average kinetic energy of the molecule inside the wax also decreases, implying that energy is releasing from the wax to the surrounding. And the energy released can be found by the equation mc delta T, where m is mass of the wax, c is the specific heat capacity of wax, and delta T is the temperature drops. However, in region 1, the state of the wax does not change. It's still in the liquid state, even though the temperature is dropping. Therefore, the separation between the molecule remains the same, okay? No change. As a result, implying that the potential energy of the molecule has no change. However, the internal energy of the wax is the sum of potential energy plus kinetic energy. Therefore, the internal energy of the wax in region 1, when it is cooling down, will decreases. At time T1, the temperature of the wax drops to T, and at this point, freezing occurs. That means the wax changes from liquid state to solid state. That is, in region 2, there are two states coexist, liquid and solid state. And the temperature T is what we call melting point of wax. You can find it from the experiment. Then what kind of energy changes when a substance is freezing? When a liquid is freezing to become solid at the melting point, there is no change in temperature. The temperature remains at T. Because temperature has no change, therefore the average kinetic energy of the molecule, of course, remains unchanged. However, the separation between the molecule in the liquid state is larger than that in the solid state. Therefore, the potential energy of the wax, in this case, will be decreasing. Which means that when a liquid is freezing, the internal energy, which is the sum of kinetic energy and potential energy, will also decreases. At a time T2, all the wax has solidified. That means all the wax changed from liquid to solid already and become solid. Therefore, in region 3, the temperature of the solid state wax decreases. That means in region 3, it is solid state. The change of energy in region 3 is the same as that in region 1, except that the state is solid. In region 1, the state is liquid. If we wait for sufficiently long time, you will see that the temperature graph will reach a constant value eventually. The reason is that when the temperature of the wax cools to a temperature equal to the room temperature, okay? At this moment, there will be no decreasing in temperature anymore. We say thermal equilibrium has reached. In this example, let's see how to change ice at negative 20 degrees Celsius to steam at 100 degrees Celsius. The first step is to heat up the ice to make it become ice at 0 degrees Celsius. This is the melting point of ice. In step 1, the ice is still at solid state. In the second step, we need to change the state of the ice to become water at its melting point 0 degrees Celsius. During this process, the state of the ice changed to liquid, which is water. In step 3, we need to change the temperature of water to become its boiling point 100 degrees Celsius. Throughout step 3, water is still at its liquid state. The last step, which we say is step 4, we have to vaporize the water at 100 degrees Celsius to steam at 100 degrees Celsius at its boiling point. Okay. Step 2, we say is smelting. Step 4, we say water is vaporizing. Throughout all the steps, energy are absorbed by the ice to change it from negative 20 degrees Celsius to steam at 100 degrees Celsius. The energy need in different steps is E1, E2, E3, and E4. You have learned how to find E1 and E3 in Chapter 1. E1 equal to mc delta T, where m is the mass of water or mass of ice. C is the specific heat capacity of ice. In this case, okay, it is the specific heat capacity of ice, which is 2100 joule per kg per degree Celsius. Delta T is the change of temperature. In this case, is equal to 0 minus negative 20, which is equal to 20 degrees Celsius. For E3, again, we use mc delta T to find the energy required. In this case, C is the specific heat capacity of water, okay, which is equal to 4200 joule per kg per degree Celsius. You have learned that before. And change in temperature, okay, the temperature change will be 100 degrees Celsius minus 0 degrees Celsius, which is equal to 100. By adding E1 to E2 to E3 and E4, okay, this total energy is the energy need to change the ice at negative 20 degrees Celsius to steam at 100 degrees Celsius.